Today we'll be considering question 8, ending group 1 in chapter 1. This problem is as follows. Is the set of all monotonically increasing sequences of natural numbers, which are sequences of natural numbers a nu, such that a nu is less than or equal to a nu plus 1, countable or not? And the question is why. Take a couple seconds to try this out for yourself. I'll give you a hint and then we'll move on to the solution. So for some hints, we should just try to recall what a monotonically increasing sequence of natural numbers look like. So a very simple one is 1, 2, 3, 4. But we also have the case of 1, 1, 1 indefinitely, and this also extends. Next hint is about proving the countability of this. So if you want to prove that this is countable, you need to show that you can create a listing of them such that every element is included. And you can do this by decomposing into unions and trying diagonalization, or just by doing it directly. Alternatively, if you want to prove that it's not countable, you need to generate a sequence. And you need to show that you can always generate a sequence no matter the listing, such that that sequence is not in the listing that's given. And some ways of doing this are by considering elements in every sequence and showing that a new sequence is different from every one of those, so it cannot be included in the listing. So take a few seconds to try that out, and then I'll give you another stronger hint in a second. A significantly stronger hint is that this set will not be countable, so you need to prove that this is not countable, that there is no way of counting this sequence, and you should do this by generating a sequence that will not be in your listing. All right, let's begin. So for this, I'm going to use these as our example sequences. We're going to go by showing that this is not countable. So I'm just going to write a few sequences here, and we'll see the mechanism by which we will generate this. And let's let our next sequence be the sequences of powers of 2. So here's a proposed listing, and this is just for example. Perhaps your listing is more convoluted than this, but for now this is just an example. And now we're going to generate a new sequence of numbers. So our first number will be the first element of the first sequence, but plus 1. So in this case, that'll be 2. I will note that this will never match the first element. This sequence we generate now will never be the same as the first sequence in our listing because it's different in the first place. These could not be the same because the 1 and the 2 are unequal. And for instance, this was a 4 instead, we would write a 5 as our first new element. For our second position, we're going to do the same thing we just did, as in the, but in the second slot instead. So we look at whatever's in the second slot here, and we add 1 to it, with a particular caveat. Namely, that if the number we would generate by that method is too small, then we should generate a number that is equal to the previous number on our list, since we're allowed to have monotonicity. So we're going to see that in a second, but for now, we have a 1 here, so we're going to write a 2 here. So we see our new sequence could never match the second one because it differs from the second sequence in the second position. Next, let's consider the third element in our sequence. In this case, we have a 4, so our next element is going to be a 5. And now let's introduce the fourth element in our sequence, which will just be the sequence of all 2s. So we'll note that in the fourth position there's a 2 here, and this 2, if we add 1 to it, we would generate 3. But the sequence we're generating now has to also be monotonic. Therefore, we would not use a 3, but instead jump up to whatever the previous number was. This is going to be a 5. And continue in this way. For instance, suppose we had a sequence where there was a 4 in the 5th position. Well, we're going to add 1 to this, and so it's different, and then if that is less than our previous term, we're going to go up to whatever our previous term was. But if it's greater than or equal to, we're just going to keep it. So in this case, that's a 5, we're going to keep it. And finally, suppose we had a sequence where we had a 3 in the 6th position in our 6th sequence. Then, if we add 1, we generate a 4. That's too small, so we're going to go up to our previous number. So that's going to be another 5. This sequence we've generated now is different from the first sequence in the first place, the second in the second, the third in the third position, the fourth sequence in the fourth position, and so on and so forth. So this is a new sequence and we'll also note that by our method of generation, this is a monotonically increasing sequence. So you have a monotonically increasing sequence that is different than every single sequence in our supposed listing, but because it's different from all of them, it can't be in the listing. Therefore, we have an element that does not fit in our listing. But we have an element that's not in our listing. That's a contradiction because we said we had a listing of every monotonically increasing sequence. With that contradiction, our assumption that we were even able to list all the monotonically increasing sequences in the first place is false. And so we have that it is not a countable set. To recap the overall structure, we assumed that there existed a listing of all the monotonically increasing sequences. If there exists such a listing, then it's countable, so we're done. We suppose that there exists a listing, but then we showed that in this listing, we could find a sequence that should be in the listing, namely this sequence by our method of generation, but is not in the listing. This is a contradiction, though, because we said this listing should have every sequence of the appropriate form, except it doesn't have this one. Therefore, our assumption was wrong, and this cannot exist. Therefore, since there cannot exist a listing, it is not a countable set. So we have an uncountable set. With that, thank you.